Hey there, Math 125 fans. Going to make a quick video reminding you about trig integrals. Trig integrals are really just about substitution. There's one identity you have to remember. If you only have room in your head for one trig identity, it's this one. The majority of the time when you need to do something with trig, that's the identity you need. Now, we write it in a few different ways. Sometimes we write it as 1 minus sine squared is cosine squared. Sometimes we write it as 1 minus cosine squared is sine squared. And sometimes we divide everything by cosine squared. And what happens if you divide everything by cosine squared? Well, you get a 1. You get sine squared over cosine squared, which is tangent squared. And you get 1 over cosine squared, which is secant squared. So I have very limited brain cells. You're younger than me. You have more brain cells. But my brain can only hold that one. But from that one, I can get this one. That's all I need. I can do all these problems. How do we do it? We're trying to set up a substitution. And it turns out we really like these even numbers. Because if these are even, we can use identities to rearrange them. If it's a 4, we just have to do it twice. If it's an odd number, we're kind of in trouble. So here's the strategy. We are going to make even powers appear and then use the identities so that a substitution works. And here's how we're going to do it. We're going to yank out one of the signs. That's going to leave us sine squared. I mean, to me, this logic is really pretty. And when students, if you're just blindly following the book, you're going to get it wrong. So you need a little bit of the idea of how this goes. Why do we do that? We do that to set up a substitution. And the substitution I'm trying to set up is one, for these problems, I'm trying to set up one of these substitutions. And if I'm setting up that substitution, then I need to make its derivative appear somewhere, meaning there needs to be a sign somewhere. And I'm trying to run out of space here. Or there needs to be a cosine. So it's one of these problems where you're making a substitution appear. And in order to make that happen, you have to think about the function you want here and the derivative you want. Okay, that's what it's all about. So if I made a sine appear here, it doesn't matter if the negative's not there. We'll account for that in a second. But I made a sine here. That means I want to turn everything else into a cosine. How do I turn everything else into a cosine? I use this identity. Sine squared is 1 minus cosine squared. So if you don't have the plan, it's very unusual what you're doing. But if you know that, oh, I'm just trying to set up a substitution, then it makes total sense to write 1 minus cosine squared of x, sine of x. So for me, I like these problems because it's not that much for me to remember. I'm not having to look at a note sheet with 50 different cases. It's just one idea. I'm setting up a substitution. In this case, it's the cosine substitution. So it's going to be 1 minus u squared. And then, unfortunately, sine dx is not quite the same. There's a negative, but I always just write negative 1 du. Distribute the negative, you're done. Okay, what about this one? This one's odd. So we're going to pull out one cosine. And after you do a couple of these, you start to go, I don't even need to write that intermediate step. I just need now to turn everything else into a sine. So you can see how I think through it. So if I ever forgot these methods, I would just write down the function and its derivative and say, how do I make a substitution appear? And so I think this is a situation where I do a better job than the book. Because I think the book gives these tables. I know why it does it. But I think by having the tables, it makes it more complicated. Because what I'm going to be left with is a cosine squared, which is 1 minus sine squared. But it's hard in a book to say what I'm doing. I have the advantage of trying to guide my students. Then you distribute, integrate, done. Okay, what about these ones? So these ones switch strategy a little bit because of the derivatives. The derivative of tangent actually has an even number in it. It's secant squared. So the question becomes, I've done it again. I've ran out of space. I don't know if we're too small to see. I have one special one down here you see popping up. But which one of these can I pull out a secant squared and still make it even so I can use my identity, this one. So that's why it's a different strategy, because I don't want a secant, I want a secant squared out here. And now I've made my derivative up here, but I need to turn everything else into a tangent. Now one of the things already is a tangent, so that's great, but there's still a secant squared here. But secant squared is 1 plus tangent squared. And then we have it. So this is exactly what I do in class. I lay all these out, and I say this is y. And then we distribute, we integrate, done. What about this one? This one I can't pull out a secant squared, because if I do, there's still going to be a, sorry, this is supposed to be secant. People are like, what is that one? That one you need to rewrite it either all in terms of sines and cosines or in terms of secants and tangents. But that's another story. Okay, so du is secant tangent. This tends to work well if tangent has an odd power, which it does here. So we're going to pull out a secant and a tangent to make the derivative appear, and I'm just trying to get through this quickly. I'm probably spending way too much time, but I hope you're getting something out of this. And then I need to turn everything else into a secant. How do I do that? Tangent squared is secant squared minus 1. Again, I'm making this video for someone that has supposedly already learned this, and I'm trying to give you a refresher or a bit of perspective. So that's why I'm not doing the full reteach. Okay, so you distribute, integrate, done. At the end of all that, you realize there's a few holes. And the few holes are integrating secant, but we give you that one in the section. Integrating secant cube, but we also give you that in the section. And then there's one other key situation, which is what do we do if we have an even power of sine or cosine or both? And that's when we need a new tool. And the new tool is this. We need that cosine squared of x is 1/2. So it turns out, yes, we do need a couple more identities to put in our head. Okay, now these two things look similar. It relates a triangle with twice the angle to a triangle with the original angle. I, as a student, could never remember exactly which one had the plus and minus, so I just learned to plug in a number to each one. So I learned that if I plugged in 0 here, I get a 1. If I plug in 0 here, I need to get a 1. So this has to be a plus, because it needs to be 1 plus 1 over 2. So if you have the general format of identity, you can always plug in a number and see what you get. Okay, anyways, what you do is you bang this over the head with the half angle identity until the answer pops out. It's not pretty, but it works. And you just have to know that that's the special case. So you would not be doing this in the cases we just discussed. So this is the half angle, this is the half angle. So it's going to be this times itself. I'm going to write a 1/4 out in front because a half times a half. Maybe I'll do it up here because I'm trying to go quickly. And then I'm going to have to, unfortunately, monkey face this out. That looks like a monkey face. See, the nose, the mouth, eyebrows. Okay, here we go. So it's 1. We're going to get plus 2 cosine of 2x. Plus cosine squared of 2x dx. This one we can do now. This one we can do now. Oh, shoot. This is why I say we bang it over the half angle identity till the answer pops out, because we use the half angle identity again right here. This is 1/2, 1 minus, 1 plus. See, I tried to forget it again. And this is the one that students always ask me questions about, but I'm not going to put a 2x here. I thought you said that was a 2x. Well, in this case, there's a 2x here, and so this is going to be a 4x. Then you integrate and you're done. So that's the idea of that section. I'm going to stop there. Check out my notes if you want to see more of those, but I think of trig as clever substitution in all cases, except if it even powers a sine and cosine. Hope that helps.